Good morning, everyone. This is Miss Xiao here, and today I am going to do a short presentation with regards to the topic of primes, highest common factor or HCF, lowest common multiple or LCM, and their applications. This is the very first topic in the secondary one, G2 and G3 syllabus. So without further ado, let's take a look at the handout. There'll be 10 questions in all. So thereabout, the explanation to the questions will take about an hour. So let's dive in. Now let's take a look at the questions here. For question 1, it starts out by saying, written as the product of its prime factors, 756 is equals to 2 to the power of x multiplied by 3 to the power of y multiplied by 7. Find the value of x and y. Now, if you look back at the question, 756 is basically being split up into its prime factors. So therefore, this question requires us to do prime factorization of 756 so that we can find the powers of x and y respectively. So in our working column, let's do the prime factorization of 756. So just a recap, 756 will have to be divided by its smallest possible prime factor. Noting that it is an even number, we will start with the smallest possible prime factor, which is 2. So we will get 378. Continue to divide by 2, we get 189. Because it is now an odd number, we have to move on to the next possible prime factor to divide, which is then 3. Continue to divide by 3, continue to divide by 3, and finally, we divide it by 7. So 756 can be broken down into 2 times of 2, 3 times of 3, and 1 time of 7. Putting everything in context, 756 is equals to 2 squared multiplied by 3 cubed multiplied by 7. Now, before we write down the answer, it is always good for us to do a check. So bring out your calculator, okay, and always press in the values that you have found in the prime factorized mode to see whether it multiplies to give you 756. So yes, and therefore x is equals to 2 and y is equals to 3. Now let's move on to the next question. Find the smallest possible positive integer n such that 756n is a perfect square. Now, just to recap, an integer is a number that does not consist of a fraction nor a decimal. It is positive, it can be negative, and it entails 0 as well. So it is the set of numbers that are whole. For example, -1, 0, 1, 5, so on and so forth. Okay, and it does not consist of decimals nor fractions. Okay, so with this in mind, 756 being a n times n, being a perfect square means that is 756 multiplied by the value of n. Now, before we can find what n is, it will be good for us to put down the prime factorized form of 756. So I will replace it with 2 squared multiplied by 3 cubed multiplied by 7 multiplied by n. Okay, now we should be able to find the value of n. Let's see. It is a perfect square. So perfect squares means that for each and every one of the prime factors, the powers, okay, which is the number at the top, have to be a multiple of 2. Let's take a look at the first prime factor. We have 2 to the power of 2. Now the power is already 2. it is a multiple of 2, so we do not need to multiply any more times of 2 to 2 squared to get another square number. So this is done. Let's take a look at 3 cubes. 3 cubed, the power is 3. We need to bring it up to the power of 4 so that the power becomes a multiple of 2. So we need to multiply 3 cubed by another one more time of 3. And that one more time of 3 will go under n. Moving on, we take a look at 7. 7 is a standalone number with no power written. When there's no power written, it is always the power of 1. So in order to bring this up to power of 2, which is also a multiple of 2, we need to multiply 7 to the power of 1 by one more time of 7, so that these two values multiply to give you 7 squared. Hence, n is made up of 3 and 7. So from here, let's compute the value of n. So n equals to 3 multiplied by 7, which is 21. Moving on, let's take a look at question 2. When written as the product of their prime factors, p is 2 to the power of 6 multiplied by 3 to the power of 3. Q is 3 to the power of 4 multiplied by 5 to the power of 2. Now find the cube root of p. This is p. You would know that the cube root of something, of a number, is the opposite of what we want to find, which is the cube. Okay, so when we know that something is a cube number, the powers of each prime factor have to be a multiple of 3. Hence, to find the cube root means that we have to divide each power of the prime factor by 3. So, noting that 2 being a prime factor, it has got power 6. When we divide 6 by 3, we end up with 2. And 3 to the power of 3, the power gets divided by 3, we will have 1. So from here, let's compute, and we end up with 12. Okay. Now, alternatively, we could do it another way. Since we know that p is 2 to the power of 6 multiplied by 3 to the power of 3, hence, in order to find the cube root of p, sorry, let me just put this one down. We want to find the cube root of p. Let's write 2 to the power of 6 and 3 to the power of 3 in terms of a cube number. Let's wait a while for the pen to load. Okay, so once you see this, the cube and the cube root basically neutralizes each other. That means the cube and the cube root will be gone at the same time. So therefore, our answer will be 2 squared multiplied by 3, which gives 12. Following that, find the LCM of p and q, giving our answer as the product of its prime factors. So in order to find the LCM of p and q, we have to put down all prime factors and choose the higher power of each. So what are the prime factors here? We have 2, 3, and 5. And the higher power, 6, 3 to the power of 4, 5 to the power of 2. So would this be our final answer? Yes, because the question wants us to give our answer as the product of prime factors. So this will be it. Finally, let's take a look at the last portion, C. Okay, and it says find the greatest number that will divide P and Q exactly. What exactly is the question asking? Well, the word greatest suggests highest. And the words divide exactly mean divide equally. So when P and Q are both divided equally, we are actually looking at its factors. So what have we learned that has got the words factor and highest? Well, it's HCF. So this question is essentially asking us to find HCF of P and Q. So therefore, HCF would be to write down the prime factor that is in common between P and Q, which is 3, and the lower power. And for this question, let's multiply it out because the question did not ask us to leave our answer as the product of its prime factors. So answer is 27. Now, moving on, let's take a look at question 3. When written as the product of its prime factors, 4,200 is 2 to the power of 3 multiplied by 3 multiplied by 5 to the power of 2 multiplied by 7. So part A, write 4,410 as the product of its prime factors, leaving our answer in index notation. So without further ado, let's find the prime factorization of 4410. So we divide by 2, we get 2205. Divide by 3, we get 735. We divide by 3 again, 245. Divide by 5, 49. Divide by 7, 7. Divide by 7, we get 1. So 4,410 is equals to 2 times 3 to the power of 2 times 5 times 7 squared. Let's do a check. That's right. So the answer will be 2 multiplied by 3 squared multiplied by 5 multiplied by 7 squared. Next, let's find the LCM of 4,200 and 4,410. We will put down all prime factors and the higher power. So we have 2, 3, 5, 7. Now between 2, the higher power is 3. Between 3, the higher power is 2. Between 5, the higher power is 2. Between 7, the higher power is 2. Okay, and the question wants us to leave our answer as a product of prime factors. So this will be the answer. Following that, find the smallest positive integer value of x such that 4,200x is a perfect cube. Cube number. Okay, so for cube numbers, the power of each prime factor must be a multiple of 3. So let's break 4,200 into its prime factors. Okay, and let's decide what x is made up of. So perfect cube, all powers are multiples of 3. 2 to the power of 3 is already a cube number, so we don't do anything to that. We don't multiply any more times of 2. Now 3 is a standalone, power is 1. We will need to multiply two more times of 3 that will come under x, so that these 3 times of 3 when multiplied together will give you 3 cubed. And 5 squared, we need to multiply one more time of 5 to 5 squared to make 5 cubed. So we can see from here that x is equals to 3 squared multiplied by 5. So that will be our answer as a product of prime factors. Did I make a mistake somewhere? Now let's go back to our marking. Okay, let's take a look here at 7. We've missed out one number. So as we missed out one number, we come back and let's take a look at it. It's a standalone power 1. We must multiply one more time of 7 to it to get the answer. So our answer is actually 3 squared multiplied by 5 multiplied by 7 square. Another mistake. Okay, sometimes I do make mistakes when I'm tired. Okay, now let's take a look at question 4. Dylan has 180 sweets and 120 chocolates to distribute to his friends. He needs to ensure that every friend receives the same number of sweets and chocolates. What is the maximum number of friends who will be receiving the same number of sweets and chocolates? And how many sweets will each friend receive? Let's see. We have a total number of sweets and chocolates, and we're not going to buy more of them, so it's fixed amount. And Dylan is going to give sweets and chocolates to his friends such that each of them will have the same number and is the maximum number of friends involved. So maximum we associate with the word highest. Same number we will associate with the word factors because it's going to be split up. So HCF of 180 and 120. So let's do it this way. I'm going to label it first. Okay, and let's find HCF. Okay, so HCF will give you the total number of friends at the max. That will give us 60. So 60 friends. How many sweets will each friend receive? Okay, so let's take a look. There are 180 sweets altogether, going to be divided by 6 amongst 60 friends, and each friend will receive this amount of sweets. So 180 divided by 60 equals to 3. Each friend will receive 3 sweets. Now, let's take a look at question 5. Question 5 says it is given that 120 is equals to 2 cubes times 3 times 5 and explain why 120 is not a perfect square. Okay, we know perfect squares must have powers that are of multiplication 2, right? If you look at the prime factors here, the powers show 3, 1, and 1. Definitely is not a perfect square. But how do we go about explaining that? Okay, so what we can do is we can mention that the powers are not multiples of 2, and therefore it is not a perfect square. Okay, so I shall write it this way. 120 is not made up of the products of prime factors that are of a multiple of 2 and hence 120 is not a perfect square. Okay. Now, next question. Write down the smallest positive integer n such that 120n is a perfect square. We have done a few questions of this. Basically, the structure is a bit different, but the question is essentially the same. Let's now change 120 into 2 cubed times 3 times 5 multiplied by n. For a perfect square to exist, you realize that for 2 to the power of 3, we need to multiply it by one more time of 2 to make it 2 to the power of 4. 3 standalone, we need to multiply it by 3 to make it 3 to the power of 2. And for 5, we need to multiply it by one more time of 5 so that we can get 5 to the power of 2. Okay, so for this question, n is 2 times 3 times 5, which is 30. Okay, next question. Express 300 as a product of its prime factors. Straightforward question. Let's do our working. Divide by 2, 150. Divide by 2, 75. Divide by 3, 25. Divide by 5, 5. And divide by 5 again, that's 1. 2 squared, multiplied by 3, multiplied by 5 squared. Let's do a double check. That's right. So from here, answer will be 2 squared multiplied by 3 multiplied by 5 squared. Now find the LCM of 120 and 300. Okay. 120, the breakdown has been given to us in the question, right on top. 2 cubed times 3 times 5. Let me just put it down. And 300, we have just found it. Okay, for LCM, we pick out the prime factors that are shown in both numbers, all of both numbers, and the higher powers. So we have 2 times 3 times 5, 2 to the power of 3, 5 to the power of 2. And do we multiply it out? Yes, because the question did not indicate to leave it in index notation. So we will end up with 600. Let's take a look now at question C. So for question C, it's mentioned that Dave needs to pack 420 apples and 300 oranges equally into cartons so that no fruit is left. He wishes to issue the boxes to as many needy families as possible. Dave assumes he can pack a maximum of 20 cartons. So we have to determine whether his assumption is correct. Okay, so we know that when you have a fixed number of apples and oranges to be packed, we are looking at HCF. Okay, another clue will be the word maximum. So HCF of 420 and 300. Okay, so number of needy families. HCF will be 2 squared multiplied by 3 multiplied by 5, which is 60. And 60 is not equals to 20. Okay, so Dave's assumption is incorrect. Okay, let's see the next question. Question 6. Seems like a giveaway question. Find the value of P and Q, and we've seen that in our first question just now. So let's move on to do prime factorization. Divide by 2. Divide by 3. Divide by 5. Divide by 5. divided by 11. So 1650 equals to 2 multiplied by 3 multiplied by 5 squared multiplied by 11. Okay, and P is the power of 2, which is 1. And Q is the power of 5, which is 2. So that's what we get for our answer. Question 7. Find the following using prime factorization. So the method is restricted to prime factorization. We can't use calculator even though we are given full access to it. Okay, so let's do the working. Okay, so we will end up with cube root of 2 cube times 2 cube times 3 cube. Okay, so what happens is that the cube and the cube root cancels itself off. Okay, this one is cancelled off. And therefore, our answer will be 2 times 2 times 3, which is 12. Now we can use the calculator to double check and see whether the cube root of 1728 is indeed 12. Following that, let's take a look at finding the HCF of 42 and 98. Now, since these two numbers are not related to part A, I think it will be best if we do it by prime factorization rather than by index notation so that we can get the answer fast and accurately. Okay, so the HCF will be 2 times 3. Oh, sorry, did I make a mistake? Yes, I made a mistake. My mistake is a transfer error. Oops. Okay, so this is incorrect, yeah? Not good. Okay, so with this, let's try again. We have 42 and 98. Let's divide both numbers by 2. 21, 49. Divide by 7. 3, 7. Okay, so our HCF will be 2 multiplied by 7, which is 14. Following this, let's take a look at question 8. So question 8a asks you to find the LCM of 32 and 56. Similar to the previous question, what we will do is to do it by prime factorization together. So the LCM would be 2 to the power of 5 times 7. Okay, so work it out, it will be 224. So that's for part A. Part B, strawberry sweets are sold in packets of 32. Durian sweets are sold in packets of 56. Oh, okay. Same as the numbers mentioned in part A. Jason wants to buy the same number of strawberry sweets and durian sweets. So there might be more packets, right? Since in one packet they have different numbers. So what's the smallest packet number of packets of each of the sweets he could buy? So what we need to do is we recognize that since the LCM is 224, At the end of the day, there are 224 sweets that are strawberry and 224 sweets that are durians. So strawberry sweets are made up of how many packets? So 224 divided by 32, we will end up with 7. And durian sweets, sorry, durian packets. 224 once again, but this time round divided by 56. 4. So these two are your answers. Now moving on, question 9. A. Express 504 as the product of its factors. Oh, same thing, prime factorization. So 504 is written as 2 to the power of 3 times 3 to the power of 2 times 7. Okay, so that's our first 2 marks. Let's see the next one. Find the HCF of the numbers there. 504 and 1188, which has to split up for us. So the HCF will be 2 to the power of 2 times 3 to the power of 2. And question then asks us to leave it in index notation, so we have to multiply. Answer is 36. Find the LCM of the numbers. So we put in all factors. So we have 2 times 3 times 7 times 11. 2 to the power of 3 multiplied by 3 to the power of 3 multiplied by 7 and 11. Okay, so this will be the answer. And oh yes, we need to multiply this out, and that will give us 16,632. For C, we want to find the smallest integer p such that 504p is a perfect square. Okay, now let's replace p by its prime factors. Okay, so very quickly, p will have 2 multiplied by 7, which is 40. All right, last question. Now, this question, they ask you to write down the value of the cube root of the string of numbers in index notation. Okay, and we know that in order to find the cube root, we have to divide each of the powers by 3. So in order to find the cube root of that 2 to the power of 9 times 3 to the power of 3 times 5 to the power of 6. Okay, we divide each power by 3. We get 2 to the power of 3 times 3 to the power of 1 times 5 to the power of 2. That's it. Now, and the last question. Finally, they brought out factor 3. How do we find the 3? If you remember, when you learned factor 3, the bottom 2 numbers will multiply to give you the one on top. Okay, so I think what we can do is we could possibly start from here. Oops. Yeah, we could start our working from here. And we could also start our working from here. Okay. So 10 is a certain number multiplied by 5. We know that it's 2 times 5, that gives you 10. Here we have a certain number being 2 multiplied by 20, which gives us 40. Now, what other numbers, what other parts of the factor 3 do we consider? How about here? And here now. Okay. So 2 is split into a certain number multiplied by 10, and that's 2. Something is equals to 2 times 7, which is 14. So 3 times 14 will give us 42. And finally, these two numbers, 40 and 42, multiply to give the value of x. So the value of x is 1,680. Okay. So I hope that today's session will be something that is helpful to start you off. One takeaway from today's lesson is that the same concept can be asked in so many different ways. So never give up, even when it doesn't make sense, because sometimes we just need to dig a little deeper and realize, oh, question is asking for something you already know how to get. All right, so I will see you in the next session. Take care and goodbye.